When I first started taking seriously the idea of ancient aircraft, I was looking for the ancient engine. There may have been no possibility of finding physical evidence of aircraft because of the time scale and the fact that aircraft are built as light as possible to begin with. But if I could just show evidence that an aircraft engine existed, then the case would be made. Engine development was the major barrier to modern development of airplanes. So if there was an engine, there must have been airplanes. And if there were airplanes, there must have been science and technology. And if there was science and technology, there must have been an advanced civilization. Simple. Even though there are no airplanes carved into ancient cave walls, the origin of many symbols came from the science behind airplanes, fluid mechanics. What I'll show you now is that some important ancient symbols are based on the science that lies behind modern aircraft engines and engines in general, the science of thermodynamics. Heat causes materials to change in predictable ways, expanding, contracting, evaporating, condensing, freezing. Thermodynamics is the study of how heat converts into work, and vice versa. If you've ever wondered how gasoline makes a car move, the answer comes from thermodynamics. And the same principles apply generally to all engines that are based on the use of heat to do work, not just gasoline engines, but also steam trains, rockets, nuclear power plants, cannons, hurricanes, and the engines in all practical aircraft. Understanding the interaction of heat with materials allows one to make machines that use heat to do work. But the effect of heat on materials can be complex. The reality of heat flow is a bit counterintuitive, but I'll show that ancient people studied this topic and came to exactly the same conclusions as our modern scientists. The challenge here is to reduce arguments based on highly technical information so that non-experts can have a valid opinion on the matter. Really, the argument's based on the similarity of shapes found in ancient symbols to shapes found in modern textbooks. And it doesn't really require one to understand all the intricacies except to know why the shape is unique, why the shape is identifiable, and how the shape is based on principles of nature rather than an arbitrary design. Finding a single one of these unique shapes could be coincidence, but if you find many of these unique shapes, all from a textbook on just one subject, that makes coincidence less and less plausible. And I should add that the reason for the shapes is the use of a Cartesian plot to communicate thermodynamic ideas. The known history of heat engines actually begins in Egypt with Heron of Alexandria, who built this simple whirling arm steam engine and used it to draw open the curtains to a mechanized puppet show. Not much is known about the origin of the design, whether Heron invented it or if he reproduced an earlier design, since its name, Aeolipile, occurs earlier in other writings. But it is the first documented example of a heat engine. It's fun to speculate how history might have turned out differently if this engine had been developed to its full potential and its workings fully understood in the time of the Greeks. But its potential was not realized, and it became just another curiosity. The modern rebirth of the steam engine in the late 1600s gave rise to engines really no more sophisticated than this, and the rise of the steam engine didn't really occur until after the science of thermodynamics was born and the potential of the steam engine was realized. The first steam engines in the modern era used the vacuum from condensing steam to perform work. Later, steam pressure was used and led to the investigation of the properties of water under heat and pressure. If Heron of Alexandria had undertaken a study of the properties of water, history might have turned out very differently. He didn't study the properties of water, but someone did, long before Egypt began. Now, this is a phase diagram for water showing whether water will be a solid, liquid, or gas, depending on the pressure and the temperature. A lot of research and measurement of water over a huge range of temperatures and pressure went into the making of this graph. The shapes of various graphs in thermodynamics are inherent to the materials and inherent to the concepts. One of the important concepts is that temperature is a lousy way to quantify heat for many materials, especially water. Heat is not temperature. Temperature is the kinetic energy one molecule can impart to another when they strike. Heat is the total amount of energy one molecule can impart to others in the form of a temperature rise. Molecules don't just store energy by moving whole and bouncing around. They also spin, and they also exhibit internal motions like vibration, twisting, and flapping. This internal motion can also be released as a temperature rise when the particle strikes another particle. Some of the kinetic energy that gave rise to the internal vibrations converts back into usable heat, and some of it does not. The portion that doesn't is called entropy and is the inherent inefficiency of the material in storing heat. The total amount of heat absorbed by a material is called enthalpy. The graph of enthalpy versus pressure for water looks very different from the graph of temperature versus pressure. This is temperature and pressure. This is enthalpy and pressure. Here enthalpy is on the x-axis and pressure is on the y-axis. Those L-shaped dotted lines snaking their way across the graph are lines of constant temperature. They're called isotherms. And they're at, on this graph, even in increments of 100 degrees Celsius. Those lines are by definition straight on the temperature-pressure graph, but you can see that they snake their way across the enthalpy graph. The enthalpy is in units of joules per kilogram in the metric system, or BTU per pound in the American system. That line extending out of the top is called the critical isobar, and it's the region of a sharp transition between liquid and gas. Where the two lines are separated, the region in between, water can exist in two phases at once. Enthalpy can't be measured. It can only be calculated from a large number of measurements of temperature and pressure. The shape of this graph is inherent to water. Other materials make different shaped graphs. So how does this apply to the ancient world? Well, in the back of the book Egyptian Grammar by Lawrence Gardner, there is a list of hieroglyphic signs. It's often called Gardner's sign list, and it's the standard reference for Egyptian hieroglyphs. One of those hieroglyphs bears a very strong resemblance to this shape, and here I've overlaid it. It's the walking legs symbol. It's used to denote coming or going. I took it straight out of the book, scaled it up, and overlaid it on the pressure enthalpy graph. The legs are a close match. The right side leg with the ankle is a close match. And there's a short angled line at the top that corresponds exactly to the critical isobar. Now it's an unrealistic depiction of legs. But there are other important graphs of the properties of water. Do they occur in Egyptian symbols as well? Well, if you wanted to know everything about the behavior of water under temperature and pressure, or heat and pressure, these are the graphs you have to study. On the bottom left is enthalpy versus pressure on a linear scale, pressure on a linear scale. Top center is the same thing, enthalpy versus pressure, but the pressure is on a logarithmic scale going up to 100,000 pounds per square inch. On the top left is temperature versus entropy, and on the top right is enthalpy versus entropy. The walking leg symbol looks familiar because it's the basis of the legs on most Egyptian gods. They're shown in profile with different heads tacked onto a standard body, and the legs are in this position. If you handed these graphs to a second grader and told them to make something from them, what would they make? Maybe they would say, hey, if those are legs, then maybe you can take the entropy enthalpy plot and make it like an arm holding the y-axis of the graph like a staff. And then the log plot of pressure enthalpy can be his head and shoulder. And then the temperature entropy can be a funny looking animal face, kind of like a ram. Now we have an image of the god of steam, or as I call him, Steam Man. And he's based on the natural properties of water plus some editorial decisions. Now here's where it gets crazy. Just to the left of the main entrance to the Temple of Khnum in Karnak is a relief carving, part of a scene involving the namesake of the temple standing beside his potter's wheel. And if you overlay Steam Man on Khnum, you can see that they're very similar. If you look at any point on the superposition of these graphs with the body and head of Khnum, you'll see the shapes coincide. His horns coincide with the curved lines on the temperature enthalpy log plot, as does the general shape of the headdress and the parallel lines leading to his left arm. The tip of his horn, which is usually shown on depictions even if the horns are absent, is actually on the temperature entropy plot forming the face. The enthalpy entropy plot determines the location of his armpit and the V shape of the chest, but it also matches the curve of the arm and the termination at the wrist. Now, why would the divine potter be made of plots of the thermodynamic properties of water? Well, as it turns out, Khnum was not originally the god of clay. He was the god of the source of the Nile River, and only later became the god of silt deposited by the river. Really, Khnum is a water god. He's supposed to be a ram, but he's not a realistic ram. He has two different kinds of horns. Regular curved ram's horns on the side of his head, but also bizarre twisted and flattened horns on the top of his head that are found on no creature alive or extinct. What do the horns on top of his head look like to you? I'd suggest that they resemble steam rising from a pot of boiling water. Khnum is standing beside what is supposed to be his potter's wheel. But as we've already seen, that thing supporting the potter's wheel is Sema, which is not an axle, nor is it sheep guts, nor is it a fancy vase. It is a water spout. A water spout is a self-created thermodynamic engine that gets its power from the evaporation and condensation of water. A water spout is the most relevant natural example of the properties of water embodied in all the graphs that happen to coincide with Khnum's likeness. The final parallel I'll point out gave me an extremely creepy feeling when I first noticed it. Finding all these ancient symbols that look like modern textbook graphs was fun, but nothing really crossed the line of being too coincidental until this. Notice that Khnum is standing on a level platform and holding a long wasp scepter vertically. The X and Y axis of the diagram forming his legs have been lined up exactly with the wasp scepter and the platform, and the legs of the graph pretty much align with the legs of Khnum. The graph has been stretched vertically since Khnum's legs are longer than the walking leg symbol, but the same shape is retained overall. I reasoned that the obvious spot to align the graph would be to put the critical point at Khnum's belly button, but that's kind of inconsequential to the next point. Recall that there were lines snaking across the pressure enthalpy graph, lines called isotherms, showing the temperature and enthalpy are quite different. Those lines came straight down to where they intersected the legs on the left, then went straight across between the legs, then arched down behind the legs to the right. Now look at Khnum's legs and notice that he's wearing a skirt that forms a horizontal line across his legs. Now look at Khnum's calf. The line behind his calf arching down to the ground is called a tail. It's original and it's deliberate. The line behind the calf has just the right curve and just the right angle to be an isotherm, and it also just happens to point to the base of the skirt, which just happens to also correspond to an isotherm. This was a very creepy discovery for me. I did not expect to find this level of correspondence, especially after thousands of years of decay, distortion, and copying that occurs when images are used over and over for thousands of years. If that really is an isotherm, it's definitely at a higher temperature than the two isotherms on the modern plot, which are at 200 and 300 degrees Celsius. Since the modern isotherms are at nice round numbers on the modern temperature scale, it would be logical for the ancient isotherm to be at a nice round number on some sort of ancient temperature scale. So just for fun, I tried to determine what temperature the ancient isotherm would be on a modern scale, bearing in mind that I somewhat arbitrarily decided the critical point should be at the belly button. After enlarging and measuring the photos, I came up with an answer, and in US units, since my plot was in US units, it was at 1080 degrees Röntgen. That corresponds to 327 degrees Celsius, or exactly 600 Kelvin, which is the most common scientific temperature scale. Coming to exactly 600 Kelvin was surprising, but I think that really was just a coincidence, since there's all sorts of imprecisions in the method I used. Not to mention that what I'm doing is absurd in the first place. The Kelvin scale was arrived at in a pretty roundabout way, and it would be extremely unlikely that the same chain of events that led to its creation would have also occurred in the past. The question, though, is what would be special about that temperature versus some other? The Kelvin scale is an absolute temperature scale, meaning that 0 degrees means a complete absence of heat, and the size of the degrees was taken from the existing Celsius scale. What Kelvin did is calculate what temperature on the Celsius scale corresponded to absolute zero, which we know today is minus 273.15 degrees Celsius. That temperature became zero on the Kelvin scale, but he retained the Celsius division. The Celsius temperature division came from the arbitrary decision of Swedish astronomer Anders Celsius to base his temperature scale on the difference in temperature between freezing and boiling water, and then dividing that difference in temperature by 100. It's important to remember when trying to reverse engineer to take nothing for granted, even the number systems. Dividing by 10 and 100 is something common in a base 10 number system today, but other number systems have been used throughout history, including base 12 and base 60. So there's nothing magical about 100. Using the properties of natural, common, and easily purified materials as the basis of a temperature scale is a universal idea in the modern world, and likely would have been the basis of an ancient temperature scale too. Our modern scales are based on the freezing and boiling of water because it made sense when the scales were developed. But modern calibration of temperature instruments no longer relies on boiling. Boiling points are heavily dependent on variables such as the local air pressure. So modern calibrations are done using only freezing points because they're far less sensitive to environmental factors. Even though the Celsius and Kelvin scales are based upon the boiling point of water, no boiling water is used to calibrate the scales anymore. Instead, only freezing points are used. And chances are an advanced ancient scientist would have come to the same conclusion. To make a less arbitrary, more natural temperature scale, it would need to satisfy a few criteria. First, it would need to be an absolute scale like the Kelvin scale, where 0 degrees means an absence of heat. Second, it should be based on the freezing points of two different materials that can be measured with the same thermometer, so that you don't end up with the problem of trying to use two incompatible measuring instruments that never overlap. Thirdly, the two materials should freeze at temperatures that are in a natural ratio that also forms the degrees of the scale. I figure that since there was only one isotherm on the Egyptian god at 600 Kelvin, it must have been a very important temperature, maybe the temperature of one of the calibration points of the scale. So I looked for common materials that froze around the temperature of 600 Kelvin. Looking at the periodic table of elements, I quickly discovered that lead freezes at 600.61 degrees Kelvin. I then started looking for harmonic temperature relationships and found that iron freezes at 1810 Kelvin, a ratio of 1 to 3, and silicon carbide melts at a ratio of 1 to 5, or freezes at a ratio of 1 to 5. The more perfect the ratio, the closer the natural 0 degrees of the scale coincides with the real 0 degrees absolute. The best relationship I found was between the freezing point of lead and, of all things, the freezing point of water. which have a relationship of freezing points of 5 to 11, such that if water freezes at 5 degrees on an absolute scale, lead freezes at exactly 11. The natural ratio is close enough that 0 degrees on this scale corresponds to a mere 0.45 degrees Kelvin, and would be good enough for calculations made at normal engineering temperatures. If the scale were divided into minutes of temperature, each minute would be 0.909 degrees Celsius or Kelvin, so roughly the same granularity to the scale. A slightly better match to absolute zero occurs if you use water and silicon carbide in the ratio of 1 to 11, but it would be difficult to measure such wide-ranging temperatures with a single thermometer. So on this kind of temperature scale, human body temperature is exactly 5.66 degrees, or 5 degrees 40 minutes of temperature. Interestingly, if you measure the temperature of the sun on this scale, well, historically the number 108 is associated with the sun. Hindus carry 108 beads and do 108 sun salutations. The sun is 108 diameters distant from the earth. It's about 108 times the diameter of the earth. And on this temperature scale, 108 degrees corresponds to 5,894 degrees Kelvin. Modern estimates for the temperature of the surface of the sun range from 5770 to 6,000 Kelvin. So the temperature of the surface of the sun on this scale is 108. Another interesting parallel to mysticism or the occult is that the freezing point of iron on the scale is exactly 33 degrees. Engines that power aircraft today harness the power of fire to do work. And they do this utilizing principles first set forth by this man, Nicolas Sardis Carnot. Heat engines predated the theories of Carnot. They'd been pumping water out of mines for many years, but Carnot was the first to make useful generalizations about heat engines, so that the inherent merits of any particular kind of theoretical engine could be evaluated without actually having to build and test the engine. He didn't come up with the mathematics of heat engines, just set forth the generalizations about them that would be useful in a mathematical model. The grunt work was done by later mathematicians, but Carnot had the brilliant idea. At the bottom right are what are called indicator diagrams for heat engines, which show what the idealized engine is doing to a working fluid in order to move heat around and to extract work from the heat. The vast majority of heat engines use the expansion of gases to perform work from heat, because gases expand the most of any type of material. They're the best at directly converting heat into pressure, or pressure into heat, vice versa. The diagram on the left shows the idealized Carnot cycle of using a pure gas contained in a variable volume chamber to do work with the application of heat. Chamber volume is plotted on the x-axis and pressure is plotted on the y-axis. And the distinctive shape traced out in the diagram is inherent to the type of conceptual engine. If you start at point 1, the gas pressure is high and the volume small. The container expands while heat is added to maintain pressure in the expanding gas to point 2, where the container continues to expand to point 3 and the gas cools due to the expansion. The container then begins to contract, compressing the gas while it is deliberately cooled to maintain temperature to point 4. The gas continues to contract, compressing the gas, or the container continues to contract, compressing the gas to the high temperature and pressure of the start and the cycle repeats at point 1. If there were no heat and cold applied, the diagram would just be a single curved line between 2 points, like the behavior of a simple spring. So thermodynamics is really the science of extracting work from a spring that expands and contracts with the addition of heat. The spring being, in most cases, a gas. Because the diagram doesn't retrace its path, but instead traces out an area, this conceptual engine is viable and can produce work, and the amount of work it performs is in relationship to the area traced out. The diagram on the right shows entropy on the x-axis and temperature on the y-axis, and each corner and line corresponding to the similar corner and line on the other graph. So you can see how temperature decreases from points 2 to 3 and 4 to 1. There are many different heat engine cycles, each with its own distinctive shape to the pressure-volume plot. The Carnot engine is the theoretical ideal example, and its plot will always have this kind of tilt and prominent cusp at point 2. But oddly enough, this distinctive shape appears in ancient Egypt as a symbol for bivalve shell. It doesn't really look much like a shell, and its use, according to Gardner, is for unknown reason, like many Egyptian symbols. Egyptians at some point thought this was a shell and used this symbol to represent a shell, but what was its origin? Why would the symbol for a shell be drawn at an angle like this, rather than lying flat as shells do on the beach? I'm not going to argue that this similarity by itself is conclusive proof of ancient technology or the ancient discovery of the Carnot cycle. But the similarity of the walking leg symbol and the body of Khnum to various thermodynamic diagrams of water opens the door to the possibility that other mysterious symbols might have an origin in thermodynamics. The indicator diagram of a Carnot engine will always be at an angle like this, by its nature on a Cartesian plot, looking like a crescent moon with a big nose, and it will always look like the bivalve shell symbol. This isn't just a diagram chosen from thousands of diagrams until a match with an ancient symbol is found. It is the most important diagram in thermodynamics, and one that is published in every single textbook on thermodynamics, as far as I know, without exception. It would be great if the pressure versus volume and temperature versus entropy diagram for the Carnot cycle were both distinctive looking, so that maybe they could appear together in ancient symbols, but the temperature versus entropy diagram is just a plain old rectangle. The same concepts behind an engine that uses heat to perform work can also be turned around to make an engine that uses cold to perform work, or a refrigerator that uses work to produce cold, or a heat pump that uses work to concentrate heat. The standard air conditioning cycle is essentially identical to the cycle used by the steam engine, except moving in the reverse direction around the diagram and using refrigerant instead of water as the working fluid. The steam engine cycle is called the Rankine cycle after its inventor, and in contrast to the Carnot cycle, the fluid at the bottom of the cycle, points 3 and 4, condenses to a liquid and has to be boiled to get back to point 1. Often the pressure-volume diagram is drawn superimposed on a phase diagram of the working fluid, with a line denoting the boundary between liquid and gaseous states. This particular hill shape is found in ancient Egypt. It's supposed to mean a sandy hill slope, although the word dune would seem more appropriate. The symbol is a tad steeper than sand can really pile up. Did this symbol really begin as a representation of a sandy hill, or was that just a meaning applied to it later?